All right, guys, so welcome to our progress check review video one. We're going to talk a lot about the basics. That's where honors pre-calculus starts. So I'm really going to talk about functions for this first video, and then a bunch of different things that involve those functions. Okay, so first of all, I think we should start with just what the definition of a relation is, and then we'll move that into functions. So a relation can really be any relationship that I make between an input and an output. So for example, if you were coming into the classroom and I wrote down your name and then maybe the color of shirt that you were wearing, I could make that a relation, right? And I could map that data point. I could use a graph, I could use a chart, I could use table. That's a relation. So you can make a relation out of anything. Now, of course, I can have repetitive names because perhaps maybe I have two people named Matthew, so I could have two Matts that have different shirts. Maybe one has blue and maybe one has green. I could also have people with the same color shirt. So I could have the same output values, right? Okay. This is where we're going to start talking about what the difference is between a relation and a function. Okay. So now a function, something can only be a function if each input, so let's write this down. So a function is only a function if each input maps to only one output. So that's a fancy way of saying that each x value has only one y value, right? So basically, you can't have repetitive x values. So in this first relation, because Matt is used twice, Matt would have two different values that it could go to. So for example, if I had the function 2, 3, 4, 2, 1, 0, negative 2, 3, 4, 5. Actually, let me change that to 0 as well. Okay, so if I were to graph these points, I have 2, 0, let's say. I have 3, negative 1. I have 4, 3, maybe 2, 4, and 1, 0 as well. So if something is a function, remember this is where we ran something called the vertical line test, right? And the vertical line tests let us know if it was a function or not. So if there was anywhere you could draw a vertical line that hit your graph more than once, for example here, then this was not a function. So this particular one would fail the vertical line test. Now, you can have multiple y values. You can have repetitive y values. That does not affect the original graph being a function. Okay, so first, you want to know the difference between what it means to be a function and what it means to not be a function. So if I put up a few graphs here, okay. So we've got some of our basic functions. We've got like a quadratic or a quartic, so maybe this could perhaps be x squared. Is this a function? Yes, it passes the vertical line test, so that one's good. This one is your square root function, could be a square root function. It's not perfectly root x, but that's the parent function. Yes, this one also passes the vertical line test. This one is a y squared function, so it's like a square root function, except it has both the positive and negative, so that's why you get both sides of this. Obviously, we can see that this fails the vertical line. I cannot spell fails today. This fails the vertical line test, so that's not going to be a function. This could be like an ellipse on a slant. Obviously, that one also fails, so that is a no. This one could be like sine x or cosine x. And again, this is fine. This is a function. So just some things to look at, quick references as far as being a function. Okay. So then we talk about a function then, well, what if the forwards way is a function and so is the backwards way? Meaning like, what if we don't have any repetitive x's or y's, right? So what if we have, I'm going to leave some space here. What if each input let's do this. Let's say each output, or each input, excuse me, has exactly one output, and each output has exactly one input. So basically, there's only one match going both ways. This is called being 1-to-1. You've learned this before, so this is all just review. So this is where you want to know that you're only going to get one answer out regardless of which direction kind of you're going with your function, whether you're doing x to y or y to x. So in this first example that I have here, if these are my data points, I have no repetitive x's and no repetitive y's. This function would be 1-to-1, meaning again that there's only one input for each output and only one output for each input. Now, if I added 5, 6, then suddenly this would not be 1-to-1 because of that repetitive output. So the way that we look at this graphically is we would run something, and I'll do a couple graphs here. So I'll do a quadratic, and then I'll do like a cubic. So if we want to check to see if the original part works, we're going to run the VLT, the vertical line test. So this passes the vertical line test, so that means that from x to y, the original direction, it works. This one also passes the vertical line test, so far the original is a function. If you want to test the backwards way, which is called the inverse, which I'm going to talk about in a moment, then you're going to, if I were to invert them, it would switch x and y's places. So instead of running the VLT, you might remember that you run the horizontal line test. So the horizontal line test tests to see if y goes back to x with exactly one input. So this guy would fail the HLT. So that means it's not 1-to-1. The original direction worked, so the original one's a function, but the inverse going backwards is not a function. This guy would actually pass both, so this one would be 1-to-1. It's pretty difficult to be 1-to-1. Okay, so that's what it means to be 1-to-1. All right, so then while we're here, let's talk about inverse functions. Again, you've seen this stuff before. Inverse functions are just functions when we're working our way backwards. So for example, if my original is to take my input times 2 and add 5, if I said do the inverse of this, literally, so you would say, I multiply times 2 and then I add 5. If you wanted to go backwards, by the way, this is the way that we symbolize inverse, that it looks like to the -1, that means y inverse. We would just do the reverse, in the reverse order. So we would say instead of adding 5, we should subtract 5. And then we should, instead of multiplying, divide by 2. So what would that look like? You would first do x minus 5, and then you would divide that whole thing by 2. Now, we can find this an easier way than just kind of thinking of it logically. So one of the things that we did is we said, of course, inverses are just when x and y switch places. So your input becomes your output and vice versa. Okay. So the way that you did that, and let me do this. So then that means xy becomes yx. Okay. So the way that we did that, if you recall, and maybe you do, is we would literally switch x and y's places in the equation. So the old output becomes the input, and the old input becomes the output. Now, what I would have done here is I would have actually called this y inverse as soon as I switched it, because then I know that I'm finding the inverse. Otherwise, you're technically calling it the same y as before, and it's not really going to be the same y equation. Okay, and then you just solve for y inverse. So I'm going to subtract 5, and I'm going to divide by 2. So again, this is not like an exponent, this is meaning the inverse. So here is your function that's the inverse of this. Okay, so that's inverses. So that's how we find inverses, and that's how we notate inverses. Now these can get really busy, and we're gonna see some crazy inverses, but that's the general way that we do inverses. This little negative should look familiar because when you did sine and you wanted to solve for theta, you would do something like sine inverse, right, to get rid of sine. So that should look, this inverse idea should look familiar. Okay. All right, I'm going to come back to some inverses in a moment. But let's talk about, in the meantime, something called continuity. So if a function is continuous. Okay. So to be continuous, if I have a function, we'll go crazy. There's this little guy. Actually, I don't like that end. Let's do this. Okay. So for a function to be continuous, you should have a nice, smooth, identifiable value the entire time. Now we're going to get more intense with our definition of that in a moment. But this function here, for example, is continuous. So let's look at times when we're not continuous, because that will help us kind of come up with a definition. So what does not continuous look like? You've seen these examples before. One version of being not continuous could be like this, right? Another version of not being continuous might look like this. And another version of not being continuous might look something like this. Okay, so there are places where your graph is not defined the entire time. There's a lot of, some of you probably heard this, is there's a break in the graph. You couldn't draw the graph without lifting your pencil. Like those are probably things that you've heard in the past. Let's make sure that we know each of these types. And then eventually in calculus, you're going to get a better definition of continuity. And we will talk about that when I talk about limits in a little bit in the video. This graph, this type of continuity here, and this graph, it has a hole in it, right? It's something called a removable or point discontinuity. Again, a lot of you have termed this a hole in your graph, but technically removable or point discontinuity is the best version of that. So that's what this is called. Now this can just have a hole. It can also have a point up here as well, but basically you have this hole in your graph. So this point could exist or not exist. It doesn't matter. It's still considered not continuous. Do you guys remember what this one is called? This is when the graph is going towards a value and then all of a sudden it jumps. I gave it away. This is called a jump discontinuity. It's when your graph appears to jump because you jump from one y value to another y value. And then this last one is an asymptote, vertical asymptote. And a vertical asymptote creates what we call an infinite discontinuity because it's discontinuous along this x value infinitely. Okay. So those are 3 ways that we can be discontinuous. So if you're looking to see if a graph is continuous, you're looking to see if it has any of these issues. We come up with jump discontinuities when we use piecewise functions a lot. So, that's like this kind of a guy, like x squared plus 3 when x is greater than 2, and then you have something for the other side, like negative 17. That's typically when you're going to see jump discontinuities. Here, we're going to deal with those because in the second half, which is like rational functions, and then same, this will also happen with rational functions. Okay, so continuous versus not continuous. Okay, let's look at something called, let's review what it means to be bounded. So what does it mean if a graph is bounded? So again, let me draw some graphs. Okay. So when you think of the term bounded, like a book could be bounded, you mean that it is confined, right, by a particular something. Like in a book, you're bounded by the covers of your book, things like that. So bounded means there's a place at which you can't go past because it's kept together. So the same thing applies in math, and we're talking about y values only here when we talk about boundedness. So if I usually talk about a function being either, here's the ways we can talk about it. We can say it's bounded above, below, or just bounded in general. Okay, If it's bounded from above, that means that there's a place you can't go any higher. So it's bounded from above. You can't go higher than that. If we say it's bounded from below, that means like it stops being able to go any further below. And if it's bounded in general, that means it actually has both of these. So let's look through and see. Again, this could be an x to x squared. This could be an x to the fourth graph. Is this graph bounded? Is there a point at which it can't go any higher or any lower? You bet. And again, we're talking about only y values right here. It can't go any lower. So we would say that this is bounded below because it can't go any lower. This graph here has a point at which it can't go any higher. So it's bounded from above. So this is bounded above. This graph has little local maxes and mins, but because these guys go up and down forever, that stops it from being bounded above, so it's not bounded above. This guy stops it from being bounded below, so this is not bounded. There are no bounds to that. This guy should look familiar. A V is like an absolute value graph, and it's similar to a quadratic in the sense that it's typically bounded from one direction, and this one, because you can't go lower, is bounded from below. This is like a typical just line. And again, because this part goes up forever and this goes down forever, this would be not bounded at all. Okay. And then this guy here, this is like an ellipse, right? This guy is bounded above and below. So we just say it is bounded. Bounded in general would mean that it has both. Okay. All right. So a few more things for this video. We need to talk about something called odd and even functions. What it means to be odd, what it means to be even. Okay, so an odd function says, well, actually, let's start with an even function. So an even function says this. If your function is even, when you plug in a number, like if I plug in x, I'm going to get out f of x. I know that sounds silly, but right, if I plug in a number, I'm going to get out something. So maybe I plug in 2 and I get out 3. If your function is even, when you plug in the negative version, so again, if this was like 2, if I plug in -2, I should get the same thing I got when I plugged in the positive version. So this is the big piece of even. When you plug in the negative counterpart, you should get the exact same y value. So like if I plugged in 1 and I get out, I don't know, that value, when I go to -1, I should also get that out. Or if I go to 5 and I get this, and if I go to 5 over here, I should get that. What we notice is if we were to graph all the data points, like maybe my graph looks like this, then it would have to look the exact same thing. So on the other side of the y-axis. So you have another way of describing this, and that it's symmetric over the y-axis. That's a way you can look at the graph and tell if it's even or odd. So there you go. So it's symmetric over the y-axis. Okay, so that's an even function. You got to get the same thing out for every positive that you do for its negative counterpart. If it's an odd function, then instead, so like if I did the same thing, if I plugged in 2 and I got like, let's say 3, when I plug in the negative version this time, -2, I get out the negative version of my original y. So instead of 3 at -2, I'd get -3. And so on and so forth. If I got 1, 1, now I'd get -1, -1. And, if I plugged in 5 and I was here, then when I plug in -5, I should be the negative counterpart. So what you notice is you end up with something like this. This one also has symmetry. It's a 180-degree rotation. Sometimes they say something like it has symmetry with the origin, but it technically should be a 180-degree rotation. I mean, like that's really what's happening. So that's what it means to be an odd function. Okay, now this is easy to tell from a graph. In fact, we know some graphs right away that are even, and we know some functions that are odd. So can you think of any even functions and any odd functions that we've already worked with? And you can pause the video if you want. Okay, so some even functions could be just straight up x squared. Or even like if I did x squared plus or minus something, that would still end up being even. Now be careful, if I start moving this quadratic left or right, it wouldn't be even anymore. Okay. How about an odd function? Maybe you said x cubed. Again, if you start moving this left and right, that's going to change. But yeah, x cubed starts off odd. We have some trig functions that are even and odd. Can you remember those? The even trig function would be cosine, and the odd trig function would be sine. Okay, so what does that mean? Remember, if cosine is odd, that means if I do cos of negative x, it actually just gives me the exact same thing as the positive version. This is a big deal because we're going to use that to make questions a little easier. If there's a negative inside, it's the same as the positive version. For sine of a negative value, you don't get the same thing, but you get the negative version of the sine. And I talked to some people about this when we did graphing. So if you have a negative inside, you could bring it out front because it's the same idea. So those are helpful there. Is it a coincidence that this has that relationship? No, it's not. Obviously, even because the powers come out to the same thing. So if I took something to the second or to the fourth, it's going to come back out positive. Again, if there are shifts, that could change that. And then, of course, for the odd, same thing. If I take an odd power of a negative, it stays negative. So I can do this, for the fifths and fourths and stuff. Okay. So how do we prove if an equation is odd or even if I don't have a graph? Well, we're going to use our two rules. We're going to use the fact that if we plug in a negative and get the same thing as the original, it's even. And we're going to use the one that is, if I get the negative version of my original, then it's odd. I'm going to use those two rules to help prove. So this is my goal. So let's start with an equation that we think is probably going to be even. So let's start with like f of x equals maybe x squared minus 3. Because we said if we just shift our graph up and down, it shouldn't change it. So how do we tell? Well, first, we're going to plug in the negative version of x. So I'm literally going to replace x with a negative x, which means all you do is plug in wherever you have an x, it now becomes a negative x. And then I'm going to simplify. A negative squared would come back out to the positive. So check this out. Even when you plugged in the negative, you got the exact same thing as the original. If that happens, because f of negative x was the same as the original, it's even. There you go. So I just proved it. All right, let's try another one. Let's try f of x equals, I'm going to switch this one up quite a bit, sine x plus 3x to the fifth. Whoa. Okay. And so I'm trying to figure out if it's even or odd or neither. I mean, if it doesn't follow either of the rules, it's neither. All right, so the first thing I'm going to do is plug in a negative x, and I'm going to then compare it to the original. So I have sine of negative x. Any x you see becomes a negative. Notice I'm using parentheses like a good mathematician. And then I'm going to simplify. We know that sine of negative x is odd already, so we know that we can just bring that negative out front. That's because we know sine is an odd function. If I take a negative to a fifth power, it would stay negative. So this becomes negative 3x to the fifth. I'm not taking the 3 to the fifth because only the x is to the fifth. So it ends up negative. So now let's compare this to this. If it's odd, every single term has to be its opposite counterpart. Like if you multiplied this by a negative, is what it's saying, then you get this. That is true. So I would write, okay, well, because f of negative x is the negative version of the original, it's odd. Now these are going to get harder. Let me do one more example here. Maybe I'll do like x to the third over sine of x plus cos x. Sorry, I'm going off the paper here. Minus 3x squared. Let's look at this one. Yeah, it's intense. Okay. First things first, I'm going to start by plugging in a negative x for every single x I see. And I'm going to simplify. The top would stay negative because it's to the third. This would become a negative. Note to self, negative over negative makes this whole term back to being positive. So note to self, you got to pay attention to that. Cos of a negative is the same as cos of a positive, so I can just make that positive. And this guy, this part would become positive x squared, which would mean that that still stays negative 3x squared. Now let's look at everybody. This first term was positive, and the result was positive. So far that one stayed the same. They have to all stay the same if this is going to be odd, or even. This guy became, oh yeah, it's still positive, and this guy stayed negative. So after all that craziness, this was even. Remember, if every one isn't the same, or if everyone doesn't switch signs, then it would just be neither. Okay, so that's how we prove if it's odd or even. Okay. Now some of them do get a little bonkers. Like, let's just look at this one, and then I promise I'll stop with these. What if I had to like the 5/2? Whoa, fractional exponent. Remember that to the 5/2 just means to the 5th power and then to the 1/2 power, or of course the square root of x to the 5th. So you can think of it like that. Okay, this one is interesting. If I try to plug in a negative x, I'm going to do it to this part. So this version, because I can see this a little better. If I take a negative and I take it to an odd power, it would stay a negative. And then anybody have any issues with this? I do. Yeah, I can't take the square root of a negative. So I'm not going to be able to do this, which basically means like that graph is, I'm going to have issues with that graph, right? As far as it being an odd function. Now, I will talk about this scenario a little bit more in the future. But that's kind of that first part, but we will talk about that a little bit more in the future about how the domain of this is an issue. Okay. All right. And then that brings us to a good point, and that is talking about domain of functions, and we're going to do some operations with functions and things like that. And then I will stop for today. Okay, so the last little piece is doing operations with functions. So for example, if I give you a function, and then I give you maybe a second function, something like this. Okay, and I could ask you to add the two functions. That would look like this. If I ask you to add, you're literally just going to add this with this. If I put those two things together, the only thing that I could do is add the x term, so I could get something like this, but that's the best I could do. I could subtract. The biggest mistake people making with subtracting is that they don't subtract the whole second part, so you just have to make sure that you distribute that negative correctly to both. Oops, that's a 3. So then I'd get root x plus 2x plus 1. Okay. Now, the good stuff that I want to talk about is, and of course I could do multiplication as well. Let's talk about the ones that are interesting. Let's talk about like f over g of x. This would be division, so I'd have root x plus 5x over 3x minus 1. Now, this itself is fine. I mean, like, that's it. I'm not going to do anything to reduce it. But we're going to eventually start talking about domain and range. For now, we're just going to talk about domain. So if I need to know the domain of these functions, adding and subtracting and multiplying, you basically just have to check each part of the function itself. So like this guy is just a straight line. There are no domain restrictions. I can let x be anything I want to, no issues. Things that cause issues, square roots, denominators, stuff like that. So in this first one, I have an issue. I'm not allowed to take the square root of anything that's negative. The easiest way to do that is to take what's underneath the radical, which in this case is x, and say it has to be greater than or equal to 0. So that's this one, it's domain. So if I was doing adding, subtracting, or multiplying, I would just combine these two. So like this one is allowed to be anything, but because this one has to be greater than 0, this domain would be the most restrictive. So then both of these would have to be greater than or equal to 0. I'll do a couple of these. Now let's look at the division. The division adds a new component because although I still have to be greater than 0, because these have to both work, I have also now created a denominator. And remember, you cannot have your denominator equal to 0. So then I also have the additional, restriction now of that x cannot be 1/3. So how could I write that? Well, so I would say x can be anything bigger than 0 because of this part, but it has to not be 1/3. Easiest way to do that is with interval notation. So interval notation starts with your lowest value, which for me happens to be 0, and I'm allowed to be it, so that's why I have a bracket. And then I'm going to go up forever, 0 to infinity, except I have to leave out 1/3. So I'm just going to use a parentheses on either side of 1/3 to leave it out. So there's my domain. Okay? Okay. So that's the general idea. We're going to get into some harder ones in class and things like that, but that's the general idea for domain. Now, we have another operation that we can do with functions, and that's called composition. This is when I put functions within functions. So this is like the old, if you go to a store and you have a coupon, if you have a coupon for like $20 off your purchase, but then the store is also having like, you get 20 per, like, well, I won't use 20. You get 30% off your purchase, which if I was doing that, I wouldn't say 0.3x, I would say 0.7 because like this is how much you pay, right? So this is like the 30% off. So the question would be like, if you use them together, which one's the better deal? That's composition. Because like first you're going to do either the discount and then the dollars off, or you're going to do the dollars off first and then discount. That's composition of function. So like we write that f of g of x, or sometimes they write that f, it looks like o g of x, like fog, but they both mean the same thing. So this just means you're plugging, this guy gets plugged into the other one. So if I was doing this one means that I would take the g first. So first I'm going to take 0.7x. So I'm going to take 70% or 30% off of my total. Then you do the outer function, which means you plug this guy into f. So for every x you see, you're plugging in g. So I'm plugging in 0.7x for the x, and then I have minus 20. This is them plugged in together. Let's look at what would happen if I do f of x first, because it's on the inside. So that would mean I take the $20 off, then I do the 30%. Well, if I do the $20 off, I would have that on the inside, and then I would plug it in to g. So I'd have 0.7 here, which I can expand this. So this is going to be 0.7 times 20. So which one is the better deal in this scenario? I think you guys can see it's this guy, because you're taking more away than this one. So note to self, if you can get them to take the money off afterwards, it's always worth more, but usually they don't, especially now with technology. But this is what composition of functions is. Okay, so now that you've kind of remembered what composition of function is, let's look at its domain. Because this is different. So with composition, you first have to plug in a number to the inner function. So first if you're doing domain, you first have to check the inner function. So you check the domain of the inner function. Okay. But then the outer function gets completely redefined by g. So f will not exist as f used to exist anymore. So the cool thing is you don't check the domain of the outer function as it was, because it's no longer itself. So you check the domain of the inner, and then you check the domain of the result. And we'll see it in action in a second. You don't ever check the outer function. So let's try one. So let's say that like f is x squared, and let's say that g of x is like square root of x plus 5. Okay, so the first thing that I always do is I usually can't help myself. I kind of look at the domains, like this would be all reals. This one, remember, you have to set what's under your radical greater than or equal to 0, which means I have to be greater than or equal to -5 for g. If I was doing composition, and we'll do it both ways, we'll start with f of g of x. If I do f of g of x, that means I'm going to plug this guy into that one. So this would be equal to, there's f on the outside, right? And I'm plugging g into it. So the cool thing here is the square and the square root cancel, and you end up with x plus 5. So now let's talk domain. Well, obviously the result doesn't even have any issues. It's just linear, it's nice. But don't forget, you have to check the inner one, because that's who you would plug into first. So if I look at the inner function has the restriction of x has to be greater than or equal to 5, which means then that this has to be greater than or equal to -5. So if I did that in interval notation, it would be -5 bracket to infinity. Okay. Notice I never had to check f. I mean, it didn't have any restrictions, but I didn't have to. All right, let's go the other way. Let's do g of f of x. So this one would mean that I take f, and I plug it in here. So that's going to be root x squared plus 5. Now this doesn't cancel because you can't do the square root separately when there's addition. So I'm kind of stuck with this. Okay, so then let's look at your restriction. So f of x, the one I start with, doesn't have any, so I'm good there. But if I check the result, remember, we do not have to check g, so this no longer applies. I check the result. This guy, remember, what's under your square root has to be positive. Now here's the cool thing, check this one out. When I go to try to solve this, there are no numbers that, well, and I guess technically, I know this is an inequality, we'll talk about that later, but there's no time when I take the square root that I'm going to get out something that ends up, being negative. Do you guys see that? Like if I tried to solve this, I'll do more of these in class, but there's no time that I'm squaring something, adding 5, and it's not bigger than or equal to 0. So these are all good. So there's actually no restrictions here, negative infinity to positive infinity, believe it or not. Again, I'm going to do more of these in class, but this is the basic idea. Only check the inner function and the result. You never check the outer function. Okay. And last piece for today is how do I use composition to find inverses? So if I compose something, if f was the original function, so if f was me doing x to y, and then g was me doing from y back to x, let's think about that, what that would look like if I did them together. So if I plugged in a number and did the f function to it, I would get out y, right? If I then plug that into g, what should happen? If you plug in y, which is your new value that you're plugging in, to the g function, you should get back out x. Interesting. What if I started with g? If I started with g and if I plugged something into g, like if I plugged x into g, in theory that would map to y and then it would go back here. But it's easier if I kind of show it this way. So if two functions are inverses of each other, when you plug in, like here, let me do a point. That might help even. If two functions are inverses, so this will be original f, and then this would be going backwards. If you plug like if I started with 4, it would get me to 5. And then if I applied the inverse after that, that would mean 5 gets me back to 4. So what I want you to see here is if I start with x, do the function, and then do its inverse, I'm going to get back to x. So if you have a function and you then do its inverse, so I could do this, or I could do it the other way. I could do the inverse after I have x. That's what this would look like, right? Like I plug the inverse into the original, or if I plug the original into the inverse, you should get back where you started. So you should get out x. This is a really big deal. So if two functions are inverses, when you do the composition, you should get x. Let's look at the one that we did earlier and we'll see it in action. So like if I have the two functions 2x plus 5, and I think for our other one we had x minus 5 over 2. Now we already know that these are inverses. If I do composition with them, I should get x. Let's see. So if I plug, so I'm going to do, I guess we'll call this f and we'll call this g. So if I do f of g of x, that means I'm going to plug all of this in for x. So see the little x I have here on my outer function, that would become all of this. Now let's see what happens. Because the whole thing is divided by 2 and I have this multiply by 2, those cancel. I get x minus 5 plus 5. Woohoo! I get x. I should also be able to do it the other way. It should work both directions. In fact, you're supposed to check. So if I plug this into that one, so instead of having x minus 5 over 2, I have this whole function. Look what happens. The plus 5 and the minus 5 cancel. 2x over 2 gives me x. Yes, I get the original thing I plugged in. So if you want to check to see if two functions are inverses, if you have them given, then you can just do composition and see if they give you x. Not 2x, not 0, not 1. It has to be x. Okay, I feel like that's a good stopping point today. It's about a class worth of lecture on this. I will post the review. You can start looking at that and see how it's going. And then we'll spend next week doing some examples together. It should be fun. All right, have a wonderful rest of your weekend.